We'll proceed in innovative approach in calculus. We are in a phase of calculating maximization, minimization along a constraint line. Maximization, minimization along a constraint line. The available solution to find the maximization, minimization of two independent components x and y along a constraint line that is falling on the xy plane is Lagrange multiplier. But as usual, kind of people who are miser by nature, like me, do not want to invent anything. Invention always happens when it is highly required. It is impossible to carry with the current approach, then only invention should happen. The current approach to find maximization, minimization, it is also called extreme point. The current approach in finding the extreme point is calculate the derivative and equate it to zero. Calculate the derivative and equate it to zero. Like I always give example like productivity of the company. A company has productivity and productivity company produces products. Company manufactures products. When company is manufacturing product, then it is using two raw material. One raw material is in X quantity and another raw material is in Y quantity. Okay. If that is the case, then productivity is x to the power 2 by 3, y to the power 2 by 3. I mean 1 by 3. The productivity of the company, the equation is x to the power 2 by 3 into multiply y to the power 1 by 3. So this proves that productivity is more dependent upon x rather than y. X to the power 2 by 3 into y to the power 1 by 3. Now, if this is the productivity equation of two products, which is x in number and another is y in number. What is x and what is y? X and y can be same in number. So I have a raw material that is x in number. I have another raw material that is y in number. If that is the case, then the productivity is defined as of the company is defined as x to the power 2 by 3, y to the power 1 by 3. Means productivity is more dependent upon x than y. If that is the scenario, if that is the scenario, if that is the case, means this is what I think. So if that is the case, then when productivity would be maximum? Now anyone would say x is infinite, y is infinite. If I take if I take x as infinite and if I take y as infinite, then productivity would be maximum. Simple case, right? So to get the productivity maximum, both infinite. But there is a constraint. How come raw material can be infinite? Company is purchasing raw material. First raw material that is X in number. If one number cost alpha dollar and another raw material that is Y in number and that cost beta dollar, then alpha into X plus beta into Y is the net amount company is paying to purchase the net raw material. That should be less than equal to $3,000 or $3 million, whatever. Less than equal to 3. If I consider X price for X and Y are $1 per item, then alpha plus Y, X plus Y, alpha X plus beta Y, that is the net amount company is paying to purchase the raw material. X, X number of items where one item cost alpha dollar. Y number of items where y number of item where one item cost beta dollar. Alpha into x plus beta into y is the net amount that should be less than equal to 3. If that is the case, if it should be less than if it should be less than equal to 3, then alpha x plus beta y less than equal to 3. If alpha and beta are 1, both cost $1 per item, then x plus y less than equal to 3. This is called constraint line. This is called constraint. In mathematics, if I say x plus y less than equal to 3, rather if I say x plus y equal to 3, then it is a straight line, or this is a static vector. Now, in mathematics, someone would say productivity means z-axis. Productivity equal to x to the power 2 by 3 into y to the power 1 by 3. If that is the case, then someone can say it looks like x and y are independent to each other. Indeed, they are independent to each other. If they are independent to each other, then it looks like three dimensions, where x and y, they are independent axis, and productivity, that is fxy, function over x and y, that is small f braces x comma y braces close, fxy. Fxy or z equal to fxy, x to the power 2 by 3 into y to the power 1 by 3. So it looks like if there is a xy plane, this is x-axis, this is y-axis, this is z-axis. Looks like productivity is z, where the x and y, they lie on the xy plane. This is this is z value. If I take all the x comma y point on the xy axis, then there will be many z value as per the function fxy. If I connect all the z value, then it makes a surface. If I connect all the z value, it makes a surface. Okay. Now the question arises is, what do you want? I want that this x and y for which z value are selected, this x and y must be taken from some region in the xy plane, not full xy plane. What is that region? That region is x plus y less than equal to 3. Only x and y which satisfy this x plus y less than equal to 3, those x and y should be taken only. That's it. X and y both are positive. X and y both are x and y both are positive. In that case, this is x-axis. Consider this is y-axis. This is xy plane. This is x-axis. This is y-axis. In that case, x plus y equal to 3 is this line. Okay, where this is y-axis and this is x-axis. This is x plus y equal to 3. This intersection on the x-axis is 3 comma 0. Intersection on the y-axis is 0 comma 3. This is x plus what we want. So this is xy plane. I just rotated it. Now this is origin. If this is x plus y equal to 3, we want x plus y less than equal to 3. Whatever the hole you are seeing, whatever the hole is formed, that hole is the reason from which I need to select x and y and this line. X plus y less than 3, not like that. X plus y less than equal to 3. So on the line and below the line up to the origin, whatever this region is coming, in that region I have to select x and y. For that I have to select z. So if I draw graph of z fxy, that is x to the power 2 by 3 into y to the power 1 by 3, then someone can draw graph. So when x is 0, y is 0 at the origin, the height is 0. Otherwise, height is growing like this. Everywhere it is growing like this. If it is growing like this, then take x equal to 0, y equal to 0, that is x-axis, xz plane, create one plane here, yz plane, create one plane here, and then x plus y equal to 3, create one plane here. Whatever the intersection it is making on the surface, that region only we have to take, not any other region. Understandable? So if x plus y less than equal to 3, whatever the xy value comes, where x is greater than 0, y is greater than 0. It starts from 0, 0, 0, comma 0, and it goes till line is satisfied x plus y equal to 3. Whatever the reason coming in between, that is the set of x and y I take. That reason, if it go up and it touches the surface we draw with x to the power 2 by 3 into into y to the power 1 by 3, whatever the intersection reason is, that only we have to take as 3D. Other portion is the 3D we have to discard. In that portion, which height, so everywhere there is a, we took lot of x comma y, we satisfy x plus y less than equal to 3. Among all the x comma y, that will be infinity number, because we are taking kind of fraction number also. In all those points, which point the z will be highest? If I say, if I don't put constraint, then at what point z will be highest? When x is infinity, y is infinity, z is also infinity, there z is highest. But x must be less than x plus y, not only x. X plus y less than equal to 3. Whatever x and y value if we take, and then we go with the function x to the power 2 by 3, y to the power 1 by 3, that is the height. Among all the height we select, which height is the maximum? That is maximization along a constraint region. If I say x, now if I say my constraint is x plus y equal to 3, not x plus y less than equal to 3, x plus y equal to 3, then it is a maximization along a constrained line, that is x plus y equal to 3. If it is x plus y less than equal to 3, then it is maximization along a region, that region on xy plane is confined by y equal to 0, that is x-axis, x equal to 0, that is y-axis, and x plus y equal to 3. Whatever region is coming, in that region, what is the maximum value? Okay, this is maximization along a constraint region, along a constraint line. So Mr. Lagrange, he has provided the proof, but we decided to go by the traditional way of calculating maximum and minimum, that is derivative, and setting the derivative to 0. So if I say dy by dx equal to 0 and try to find the extreme point, that is maxima or minima, that is the extreme point that I am trying to find, then actually we are trying to dy by dx equal to 0. Okay, dy by dx, if I take two dimensions, okay, so as I always say, that if I take two dimensional, what is directional, what is a kind of dy by dx? If consider this is, okay, so consider this is x-axis, this is x-axis, this is y-axis. Consider this is y-axis, x-axis, y-axis, x-axis, y-axis. Now this is x-axis and this is a equation of a curve, two dimensional. Okay, now anyone would ask, I'm repeating this. So anyone would ask, where is the maximum point? This is the maximum point. Certainly not. This is maximum point. I mean, this is not generic. This is maximum point with respect to x-axis. My axis is here. Where is the maximum point? Maximum point is here. This is the axis now. Where is the maximum? Maximum point is here. If this is the axis, where is the maximum point? Maximum point is here. Maximization, minimization, when we calculate, it is with respect to some line. Dy by dx, maximum value in y with respect to x-axis. Here, we are trying to calculate dy by du, maximum value of y attained along any vector u. dy by dx means dy by di, I vector, that is x-axis. That is a special case of derivative. Actually, the actual term is directional derivative along a vector. Directional derivative along a vector. That is a generic term. If I say dy by dx equal to 0, then we are trying to find maximization, minimization along a vector, that is I vector, or along x-axis line. Y equal to 0 is the equation of the line. Now here we are trying to find maximization, minimization with respect to a line x plus y equal to 3. Maximization, minimization can happen in between also. So if I have x-axis and y-axis, I mean, if I take the function x to the power 2 by 3 and y to the power 1 by 3, and then this is x-axis and this is y-axis. Okay, if this is x-axis, this is y-axis. In that case, if I take maximization, minimization, if I draw a graph of a surface, surface can anywhere it can reach maximum, anywhere it, like a mountain. This is what example I give. That is a pure case of maximization, minimization. All the peak in the mountain, they are 3D maximum point. There is one 2D maximum point, like this is two-dimensional maximum point. That is three-dimensional maximum point. Or if someone go deep in the valley and then mountain, the value, the deepest point is the minimum. So that is maxima and minima. That is the concern over three dimensions. We are trying to find maximum value in xy plane, in the sense what is the value of x and y for the equation x to the power 2 by 3 into y to the power 1 by 3, where this function x to the power 2 by 3 into y to the power 1 by 3 would be maximum. This is what we are trying to find for a value x comma y, or set of value x comma y. For this will be maximum. If this is xy plane, this is x-axis and this is y-axis, then this is x plus y equal to 3 line. So if I draw a surface based upon that function, if that surface attains maximum value below this line only, it is possible that it would attain maximum below this line only. Okay, but if it attains maximum, okay, but like the equation what we are taking, x to the power 2 by 3 into y to the power 1 by 3, it doesn't look like it will have any local maximum. It has minimum 0 at x equal to 0, x comma y equal to 0 comma 0. Otherwise, in first quadrant, it looks like it keeps on growing only. If it keeps on growing, then above this line, x plus y equal to 3, above this line, if I take a plane, then that surface is passing through that cutting that plane. When it cuts that plane, at what position z is the highest? This is what we are trying to find. At what position z is the highest? Knowingly, unknowingly, we are trying to find maximization, minimization along a axis, along a vector that is formed by line x plus y equal to 3. Okay, so we are trying to find maximum and minimum along a vector that is formed by x plus y equal to 3. If that is the case, then to find the maximization, minimization along vector u is nothing but gradient vector of the algebraic equation dot unit vector of the vector u along which we are trying to find maximum or minimum. Okay, so that is the scenario. There we are trying to find maxima or minima. If it is not understandable, then what we will do is we will kind of cut down this 3D we are taking, right? 3D will cut down into contour line or leave it. I believe this is what I can do. Okay, so we are taking 3D graph fxy, function over x and y, is x to the power 2 by 3 into y to the power 1 by 3. That is the 3D surface it would form. Let's cut this 3D surface at any height. If I cut this 3D surface at any height, then I can draw a contour on xy plane. that is x to the power 2 by 3 into y to the power 1 by 3 equal to any height, any constant, then it forms a kind of, then I have to find a curve on the xy plane that satisfies this x to the power 2 by 3 into y to the power 1 by 3 equal to some constant. Consider it is 2, equal to 2. That will be typically some curve someone will draw on xy plane where x and y is set of points which satisfy this equation x to the power 2 by 3 into y to the power 1 by 3 equal to 1. Or someone is more intelligent, then he will say y to the power 1 by 3 equal to 1 by x to the power 2 by 3, or y to the power 1 by 3 equal to x to the power minus 2 by 3, y equal to x to the power minus 2, y equal to 1 by x square. Now keep taking x value something 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 and get the y value and then draw a curve. Now that curve if I draw, if this is x-axis and this is y-axis, then this some curve it will draw. And I have a line that is y equal to x plus y equal to 3. Okay. Now this curve, if I draw this, consider this curve is like this. Consider this curve is like this. And this is x plus y equal to 3. Okay. Now let's increase this curve. Now I had taken x to the power 2 by 3 into y to the power 1 by 3 equal to 1. Let's grow it 1 to more so that this curve what it is drawing, it touches this line. When it touches this line, then when it is touching this line, at that moment, when it touches the line, at that moment, then this line is tangent to this point. That's it. Maximization, minimization is nothing but the point where dy by, if I calculate dy by dx, consider this is x-axis. If I calculate dy by dx, everywhere dy by dx means tangent. What is the moment where tangent will is parallel to the x-axis? What is the moment where this tangent is parallel to the x-axis? That moment it is maxima or minima, or dy by dx is 0. The moment if I calculate dy by dx, that is the slope, that is the tangent. Everywhere if I calculate dy by dx will come in algebra. Set whatever the x is, you will get the actual slope at that moment. If I keep calculating dy by dx, one moment will come the dy by dx, the slope will be exactly parallel to the x-axis. Okay, that is dy by dx, and that will be 0. Because this x-axis is nothing but y equal to 0. So at that moment dy by dx means at that moment if there is some fluctuation in x, y will not fluctuate because it is parallel to y equal to 0. At that moment we found the maximum point or minimum point. Again dy by dx is not parallel to x-axis. If I am taking this as constraint line, this is x-axis, this is y-axis, this is x plus y equal to 3. If the contour I am drawing x to the power 2 by 3 into y to the power 1 by 3 equal to some constant, that contour diagram is touching this line, means this line, if I calculate dy by du, means this line, if I calculate tangent at this moment where it is touching means this line x plus y equal to 3 is tangent at this moment, the contour. If it is tangent means if I take this as x-axis, consider this is x-axis, then this is the moment where this point is extreme point. This is minima or maxima, I don't know, but this is extreme point. So dy by dx is 0. If this is x-axis, then if this point is touching x-axis at this moment, dy by dx is 0. This is not x-axis, this is some u vector, then dy by du is 0. This is directional derivative. dy by du is called directional derivative along any vector u, whereas actually x-axis is here. This is another axis whose vector is u. X-axis vector is I vector, y-axis vector is j vector, and z-axis vector is k vector. dy by du, change in y with respect to one unit change we see along the u vector. That is nothing but the whatever the gradient we have taken, whatever the contour we have taken x to the power 2 by 3 into y to the power 1 by 3 equal to constant. If this is the algebraic equation, I have to find gradient vector for this algebraic equation. Dot unit vector along the vector for which we are calculating the directional derivative. Okay, dy by du, directional derivative along a vector u. Gradient vector of the algebraic equation dot product unit vector of the vector along which we are trying to calculate the directional derivative. Okay, so this is the in-depth analysis. Now we calculate. Past video we have calculated. So we can take any example. If I take this example back, now this session is for actually 4 dimensions. But anyway, we will proceed with this fundamental into 4 dimensions. So here someone can try. Now the gradient vector for x to the power 2 by 3 into y to the power 1 by 3 is 2 by 3 x to the power minus 1 by 3 y into 2 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3 j. That is the gradient vector dot product with the unit vector. What is the vector equation for the line x plus y equal to 3? What is the vector notation for this? For that we have our own formula. So we know that if like what is the vector rotation for this circle? At any point, what is the vector for the circle? Vector for the circle notation is surface vector or tangent vector at any moment. If I take any point x comma y here, then that is called position vector. From the origin, if I draw a line, that is a position vector. If I calculate derivative of this position vector, that will be perpendicular to the position vector, then this will become the actual vector we are looking for, that is vector representation of any curve. Now we have x square plus y square equal to, this is the circle. We have taken a circle. So x square plus y square equal to 1 with radius 1. Now if I want the kind of vector notation that will come as vector field here, because algebraic vector will come, then I have to first find the position vector. Any point, if I take x comma y, position vector is xi plus yj, where y is the square root of 1 minus x square. Then I have to find the differential vector for this. Then that is I minus xy square root of 1 minus x square j, that is minus xyy. Now the unit vector for this vector, so this is the vector. Okay, this is the vector we are looking, that is I minus xyy j. This is the vector. If this is the vector, then what is the unit vector? That is I minus xyy divided by 1 plus x square by y square root by the magnitude. This I have to do dot product with the gradient of what we calculated, x to the power 2 by 3 y to the power 1 by 3. If we settle it down, I believe it will become y equal to x equal to 2y. Okay, I believe so. This would become x equal to 2y. X equal to 2y. Then someone set x plus y equal to 3, x equal to 2y, y equal to 1 and x equal to 2. So x 2 comma 1 point, whatever the graph we are seeing at 2 comma 1 point, this is x axis, 2 comma 1 point, wherever it is hitting, that is the maximum value we can attain in the productivity, where the constant is that x and y I have to take below the line x plus y equal to 3. If that is the case, what about 4 dimension? 4 dimension is also called density function. 4 dimension where independent components, 4 dimension means independent components are 3, x, y, z. 4 dimension means independent components are 3, x, y and z. Dependent component is density. Like I take one kind of, okay, I have two 4 dimension. Okay, this is 4 dimension. This is 4 dimension means it looks like it is not at the same density everywhere. Somewhere density is high. If I really cut it, there will be seed portion in the middle. their density will be less. Otherwise, density is higher on outside. See here, density is even higher. It is very hard. Okay, this is density function. Like I have another sphere. So here also density is different at different point. Okay, if I really cut it, then many places inside this is surface that is hard. If I cut it, then there will be seed portion and pulpy portion of guava. So in that sense, it will be their density, it will be wherever seed is there, it will come as seed density. Whereas in between seed, whatever the material is, that is very soft. So that has another density. Whereas top part has another density. So this is called four dimension. This is called four dimension. Four dimension means if I have x, y, z point, any point, at that point density is different. Density has three independent components. Now we have come into fxyz function over x comma y comma z. In three dimension we had fxy, z equal to fxy. Now here density equal to fxyz. Okay, so that is the scenario. Now the constraint, earlier we had constraint on the xy plane. Now constraint is in xyz cube. This is 4D. So constraint is in xyz cube. Okay, and function is fxyz. Consider fxyz density function is x plus y plus z. All three are independent to each other. X plus y plus z. That is the algebraic function. Whereas constraint, earlier constraint used to be in two dimensions, like x square plus y square less than equal to 45, x square plus y square equal to 1, x plus y less than equal to 3. These are the constraints. Now constraint is a sphere, x square plus y square plus z square equal to 1. That is the constraint. Means if I take density function, when this density of is maximum, where x, y and z, they follow this equation x square plus y square plus z square less than equal to 1. They are inside a sphere. Only that reason I have to see the density. It is clear, right? This is a, this consider, this is the what I am taking now. Now this is a 4D material where each point is described as x comma y comma z, that is the position comma density. At that position, what is the density? Density is dependent upon x, y and z. X, y, z are independent to each other. In that is the case, then I'm trying to find the maximum density, the density where it is maximum. That is the case. If consider the density equation is x plus y plus z, means if you keep going away from the origin, density is growing. When density will be maximum? Density will be maximum when x is infinite, y is infinite, z is infinite. There density will be maximum. No. I cannot take infinite. X, y and z must follow this equation x square plus y square plus z square equal to 1. Something like, consider this is x square plus y square plus z square equal to 1. That is a sphere. If I push this sphere inside this is centered at the origin. And if I push this sphere inside this whatever shape it is, centered at the origin, both are centered at the origin. In that region only you have to find what is the maximum density. Means x square plus y square plus z square less than equal to 1. Whatever the reason is, that the spherical region is around the origin, if it is centered at the origin, in that region only you have to find where the density is maximum. What is your equation of the density? That is x plus y plus z. So I have to find maximization, minimization x plus y plus z, provided the condition is x square plus y square plus z square equal to 1, less than equal to 1. But since x plus y plus z keep on growing, they will hit maximization only on the surface of this sphere, that is x square plus y square plus z square equal to 1. If that is the case, Then how we can find? Now Lagrange way will be very difficult here. Now first I have to find gradient vector of the algebraic equation, that is x plus y plus z, that is the graph. I mean this is not x plus y plus z, okay? This is something different, but consider this is x plus y plus z. What is gradient vector for this? That is I plus j plus k. That is the gradient vector. Now, if I want maximization, minimization along a constant line, dot unit vector along that vector. What is that vector? That is a big question. What we have understood till now, that vector is nothing but the surface vector. If it was 2D, then that was tangential vector. If you remember, the vector we are talking, to which we have to do dot product, is the tangential vector. That first we did got the position vector, and then we did derivative or we got it. Similarly, here the constant line vector is the surface vector. But surface vector at any point, if I take surface vector, it will go 360 degree. This is surface normal vector. If this is surface, everywhere surface normal vector is different. Okay, this is surface normal vector. Whereas at any point, if I take the surface vector, not surface normal vector, then surface vector will be perpendicular to the surface normal vector. It will fall in a like plane where every direction is a surface vector. If I take a position vector and calculate the gradient of it, then certainly we will get surface vector. But surface vector will be many. Not like on 2D, it is only one along the curve. It is surface after all. Then we'll try with only two. One surface vector in xz plane, if this is centered at the origin, and this is x-axis, and this is y-axis, this is z-axis. If I cut it, this is xz plane, this is yz plane, this is xz plane, this is yz plane. If that is the case, then xz plane, what is the surface vector? In yz plane, what is the surface vector? Okay, those surface vector is the vector along which I have to calculate the derivative. Okay, I have to calculate the kind of directional derivative along those vectors. Two vector I will take. I can take many vectors, only two vectors. One in xz plane, then what? Then I'll set dz by d. I will set xz plane. Now, if I take any point P here, then position vector for this constrained volume is xi plus yj plus zk, where z is dependent upon x and y. What is dp by dx? Now earlier, if you remember 2D, then I had point as xi plus yj, where y is dependent upon x. So I substituted y with x and calculate the derivative. So here it is xi plus yj plus zk. Now I'll substitute z with x and y and calculate the derivative along xz plane, calculate the derivative along y, set it to 0 both and get it the maximization, along with the constraint as a sphere. Amazing, mind blowing, right? So for the x square plus y square plus z square equal to 1, z equal to square root of 1 minus x square minus y square, that is z. Now position vector p is xi plus yj plus zk, dp by dx, that is I plus dz by dx k, dp by dy j plus dz by dy k. One is dp by dx, I have to set it to 0. This is what we did earlier. That is direction. I'm sorry, dp by dx. What is that vector? I'm sorry, dp by dx. What is that vector? Earlier dp by dx was I minus x by yj. That is the unit vector along which we are trying to calculate the directional derivative. What is unit vector? What is the vector dp by dx? That is the vector, surface vector in xz plane. dp by dx, I plus dz by dx k. Z is the square root of 1 minus x square minus y square. dz by dx minus x by square root of 1 minus x square minus y square minus x by z. dp by dx is I minus x by z k. Now, if this is the vector, what is the unit vector? I minus x by z k divided by 1 square root of 1 plus x square plus z square. Okay. Now this vector dot product with the graph vector, gradient vector, that was x plus y plus z. Now I plus j plus k dot with this vector I minus x by z k divided by the full volume, full square root of 1 plus x square plus z square. Set it to 0. This is the way to calculate the maximum minimum. Then it will become I minus x by z equal to 0. X equal to z. X equal to z, there it is maximum or minimum. Now again try with another dp by dy, that is j minus dz by dyk, dp by dy j plus dz by dyk. Now z equal to square root of 1 minus x square minus y square. Same thing will come here also. And then when we do dot product with I plus j plus k dot j minus y by zk divided by its magnitude, and we settle down, it will come y equal to z, z equal to x, z equal to y. When x equal to y equal to z, all three are equal, at that moment it is maximum. Okay, where it will be. Now a spare equation is x square plus y square plus z square equal to 1. If I settle it down, then x 3x square equal to 1. X equal to square root of 1 by 3. Y equal to square root of 1 by 3 plus minus. Z equal to plus minus square root of 1 by 3. Okay, at that point, this x plus y plus z graph would attain maximum. This is our proof. Okay, this way you can continue to the n dimension. Please do support us. +91 is the India country code. 94831 60610. That is the telephone number. 94831 60610. +91 is the India country code. Okay, so this is the four-dimensional way. Whatever algebraic equation is, calculate the gradient vector dot, then surface vector, that is the vector along which we are trying to calculate the directional derivative. We took two surface vector. One is dp by dx and one is dp by dy. As I say, dp by dx is dancing in xz plane, dp by dy is dancing in yz plane. Anyone can take any plane. There is 360 degree up to anyone. But with these two only we are satisfied. Anyone can try other also. What about if I do dp by dx cross dp by dy? Then that is something that is a surface normal we get. That has another implication in calculating the surface area of something that we have done tons and tons, so many times we have done it. Okay, we will proceed. So this is the end for the innovative approach in calculus as far as Lagrange multiplier is concerned. Someone can, now we will proceed in other invention what we have done in calculus. So that we will see.